Yes, so today I'll be talking about noise sensitivity on equivalence classes. We'll start very simple. There are some rules. Start with an equivalence relation on n elements, and you have k many equivalence classes. If that sounds weird to you, then you can just think of these two graphs. The simple idea is just that you can think of two parallel societies or two parallel communities, and within these communities everybody knows everyone, but outside of them nobody knows anyone else. And the goal really here is to study a specific problem. So we would like to apply some noise to this initial setup, and we would like to look at the same graph, and we take each pair and flip the relation with probability p. By flip, I mean that if the relation was already there, then we delete it, and if it was not there, then we add it. And this happens with probability p. And of course there's the question, you start from this graph and you go to this other one which maybe doesn't look so nice, and you ask the question, so what happened? And this is a question we'll keep in mind, and we'll answer for this talk. So the stochastic model that we're looking at is the following. Well, if you want to flip vertices or flip edges, then you're looking at Bernoulli random variables, and this is the setup. So you define this in U noisy equivalence relation out of the original equivalence relation, and you say that if already you had this connection between I and J, then it would need to not flip in order to preserve this relation in the noisy model. And the same is said about the other case, where you have two edges which are not related. Then if you want them to be related in the noisy model, you would like to flip the edge, so to say. And so I've plotted the changes that have happened here. I've not drawn the connections that we had. So these are the additions, which are between the two equivalence classes that we have, or between the two graphs that we have. And here we had two removals. So these were the only two removals that we had, 1812 and 114. Maybe that kind of answers the question of what really happened, but I don't think that's too interesting for what we would like to do. So, what is noise sensitivity? I think this is best demonstrated with an example, which I'll go over very quickly because it's not really the core of the talk, but it gives a great motivation. So if you take a string of zeros and ones, and you have a function f that gives you 0 if the number of ones is even, is odd. Yes, it gives you 1 if the number of ones is even. So we have an even number of ones, and it gives you 0 if c is odd. Then, in that case, this function is noise sensitive. What am I trying to capture here? I'm trying to say that if we look at this string here, and let's say I flip one of the edges with probability p, I don't really know what's going to happen.
You're one of the bits, not edges, right?
Yes, edges, bits. Yes. So I apply some noise and something happens. Maybe they don't change at all. But then I don't really know, because you have this probability p of everything, every bit being flipped independently. And so you don't really know how you can preserve this parity, so to say. So if you have this channel and you're distorting these bits, it's not so safe to communicate through this channel. But if that is not clear, we can just move on immediately. So this notion of noise sensitivity was first suggested by, I believe, Regev, Kalai, and Beniamini, and they did it for Boolean functions. And here we propose the same construction, a construction of the similar taste for equivalence relations. And we say that there is a noise stability. This is how we would like to define it. If we have a recovery mechanism, we could think of an algorithm that takes the noise, like we had in the previous graph, and this probability that it actually is the correct prediction for the noisy, for the actual original graph is, as x grows very large, you have this convergence to 1. So that is really what we're looking at here. And an analog is just, so if you don't have a mechanism, if you don't have an algorithm that can, with which you can recover these equivalence relations, we say that this equivalence relation is not going to be noise stable, it's going to be noise sensitive. But in this thesis, we will show that it is not the case. So, the goal of this talk again is to supply this mechanism. What is this algorithm that we can apply to reach this outcome? And we have a small proposal, and that is the following. I would like to look at the examples first. I didn't put the examples here, so we just have to pretend that you used to have them in mind, but that's something else. So I would like to define this notion of a score, which quantifies the transitive property of the equivalence relation. Even though we have lost transitivity in the sense that not for every pair of vertices, not for every triplet of vertices, we will find the triangle that connects them, but this, in a sense, measures the loss of the transitivity that we have attained. And we can see, for example, that, and we will see that in the next slide, that when we have two vertices which are in the same class, then you have all the other elements in the equivalence relation that are equivalent to it. And so I think this is much easier if I show you the example, because I can speak until tomorrow, but then the examples are really what make the most sense. So here we're looking at the following. I've skipped quickly over this notion of a score matrix. It is just a bookkeeping system to store all the scores, so all the transitivities that you have for the vertices of the graph, or for the elements of the equivalence relation. So, the example, which is very interesting, we start with a simple equivalence relation. Everybody knows everybody, and outside of this community, nobody knows, anyone else. And from there you can see that for the green equivalence class, you have these scores that are initialized. They're also initialized with 7 because, for example, if you choose this vertex, then you have, and let's say you choose this vertex and that vertex, then you have 7 other vertices that attest to the relation between these two vertices. And so this is the setup. We start from 7, 8, 7, 7, 7. And in the case where you have the score between an element and itself, so this is the score between 1 and 1, you have an additional element, but that is not significant. It's not interesting for what we would like to do today. So let's take a look at how this initial score matrix was affected. I think that is going to tell us a lot of information. So these are some scores, for example. 2 and 3 are not in the same equivalence class, and so it does make sense that their score will be low, because if you want to apply some small noise and you apply it to this model, then you wouldn't expect to have that many conversions, so to say, because you start from 0. And the same is, the converse is true when you have two elements of the same equivalence class. So here, I think it even gained one more score. And this is the score matrix, so to say. So you have the red elements, which are in this class, and the green elements, which are in that class. Now, let's take a look at what happened to these scores. So if we're looking at the red ones, then you see that if 1 is not in the equivalence class of 2, let's focus on 1 now. So 1 was not in the equivalence class of 2, or 4, or 5, or 8, or 9, 10, 12, 15, 16, and so on. So it does really seem that this notion of a score is resilient to noise, but of course this is not a proof, and we need to make this a little bit more rigorous. And at the same time, if you look at the scores of the number 1 with the elements which are originally in the same equivalence class, then you have 6, 6, 7, 6, and so on. They're almost unchanged. They started at 7 and they've been perturbed to a small degree, but they can still resist this level of noise. And there's of course the natural question, and that is this something that we can generalize, or is this just a lucky example? Maybe I sat down before the talk and I found the nicest example I can get. Well, I did, but this is true. You have to trust me on it. Well, you don't have to. We have a proof of it. And so this is the whole score matrix. It's a 20 times 20 matrix. You can't imagine how long it took me to write it down. That's another thing. But what we have here is the following. The key observation is that whenever the elements are in the same equivalence class, the scores are very high, and when they are not, they're a bit lower. But that is not so clear. So let's do a little bit of a change. Maybe it is not very useful. Let's sort the row values ascendingly and see what we get. And we will do this, I believe, for all of the rows. And when we do this, you see this setup. You have these sharp jumps, so from 1 to 6, or from 4 to 8, or from 3 to 6. Maybe that is not so sharp, but you can perhaps more rigorously prove that it is sharp in this sense. And we will talk about this in a moment. And really, that is the takeaway from here. So this is a global phenomenon. It is a global phenomenon, and maybe we're not so lucky with one example, and the score gap is actually significant. So I would like to take a moment and stop here and ask if you have any questions, because we will move on to another part, which is the formalism of this construction. So we started with this simple idea of transitivity. It's the only natural encoding of these equivalence relations. And what we're doing right now is we are utilizing this encoding to its maximum. So if anything is unclear, please feel free to interrupt me. And if you would like to formalize this idea of a gap, because it is very tempting to just cut the relationship of one with the other elements from here on and get our equivalence class back. It is very tempting, and so let us explore this prospect together. So fix x to be an element of x1. x1 is an equivalence class. You can think of it as some graph in that case. And if we look back at the same example that we had, here I'm trying to compute the, so to say, the expected value. So if you've never heard what an expected value is, well, roughly it's just the fact that if you flip a coin 100 times, you're expected for it to be close to 50. And so we're just trying to understand the long-term behavior of this score function, so to say. And so if you have two elements which are in the same equivalence class, then you would keep both edges with probability 1 minus p. And the reason for this is because if you don't keep them with probability 1 minus p, you will flip them with probability 1 minus p. There's something that I am yet to emphasize, and that is that all of these Bernoulli random variables are independent. So these flips are absolutely memoryless. They don't care or know what the other edge has done to the other vertices. And so we have this setup here. And if you have if you have a witness to this relation between x and 1, which is, let's say, it's not a real witness to the equivalence relation, then it would contribute to the score with probability p squared. So you have this Bernoulli random variable which flips and gives you 1 with probability p, and if you do it twice, then you have something that gives you 1 with probability p squared. And that is really what it is. This is a computation that I've done. This is the expected score. And the only takeaway we need from this is one specific fact, and that is you always have a starting point, which is n1 minus 2. You can also guess that it might happen because you have 1 times 1 times, so 1 times 1 for all of the elements of this equivalence class. And this equivalence class is of size n1. So you kind of expect that this will happen. And this is interesting because it always gets so to say, a head start over the scores which are not in the equivalence class. And so let's move on with the same construction for the other case where we have two elements which are not in the same equivalence class. So this is what we have. This is x in one equivalence class, and this is x1, and that is x2. And if, in principle, they start from 0, they don't have any correlation at the beginning, their scores are completely 0 because inter relations are only existent and intra relations are not existent. Now, if that didn't sound clear, that's completely fine. And so if we would like to compute the expected score for x and 2 under the assumption that 2 is not in the equivalence relation, then simply you have p times 1 minus p for every w in this equivalence class, and this is exactly what we have here, p times 1 minus p for every w in this equivalence class. The same construction we have here, 1 minus p times p for every element in this equivalence class. And as with the first one, if you have this initial setup, then you need to flip two edges, and this costs you p squared steps. I've also computed the score between the expected score between two elements which are not related to each other. And here, very interestingly, it is, if you forget about this higher order term, it is n1 times p, which means that we can, in a sense, put a stop to its growth. So in a sense, we can let the out scores grow slower, and we can let the original in scores grow bigger. And then we have this gap, so this expected gap that we're trying to formalize. We have this intuition about it. And so here's what the expected gap computation is going to be. So as expected, why would you expect this? It's because the first expected n variable had an order of n1, and the other one had an order of n1 times p. So you would imagine that this term would dominate if you look at a subtraction of the two variables. And this is precisely what we have. This is a computation. I mean, you have to do some algebra. It's not so interesting. And the implication of this is that the gap gets larger and larger as we go on in time. And so there's this, of course, there's this critical question. So now we know that the gaps are getting larger, and that in principle, if we have some score matrix or something similar, we are able to make the cuts at the respective points. But then we need to look at the cases where we might have large deviations. So we need to make sure that the out scores, so to say, are concentrated here, and the in scores are concentrated there. So there are no jumps, so to say. So we want to cancel out these jumps. We don't want to have any jumps. And so if you look at this example, and for this you need to compute the separate variances for each random variable, the xi in hat and xi out hat, which was the expected in and out, not the expected, the in and out scores as random variables. And you have this setup. So you have something that's very similar to what we have on the board here, which is the following. So the out scores are kind of concentrated here, and the in scores are concentrated there. And they meet at this very small point. And this is just n is equal to 20. You can imagine how this would be like if we make n larger. And then we don't have this concentration, but this is the key idea. This is the key idea, is that number one, we want to make the gap as big as possible, and number two, we want to concentrate the, let's say, the in scores and the out scores, so we can separate them in the very end. And so we have this theorem, or this concentration bound by Bernstein, which says that if you have independent random variables which are bounded, and their variance is less than sigma squared, so it's less than some constant, you could say, then if you set z to be the sum of all of these random variables, so in that case we're summing up all of, let's say, the terms in xi hat, which is the gap. So we're summing all the terms of the gap, and we'll see how we apply this. Then we obtain an exponential bound. An exponential bound on the deviation of the measured sum. And that's very good because with each step you have this exponential decay, so to say. And this is more or less what we had in the previous example. Maybe it was not so clear because maybe the numbers are not so big. But this is really the key idea. So the exponential bound is very good. It's actually amazing. It's more than what we need.
So S is Z, right?
So S is Z.
So the sum, you denote it by Z, but then here you have...
Yes, that is a typo.
Okay.
Thank you for the correction. Yes. So the measured sum is precisely the Z. It's not S. And the implication here is that, and maybe I'll write this very quickly. So if you have the exponential, and you have sigma squared as small o of t squared, so it grows slower than t squared. And on the right you have something that's big O of t, and on top you have something that is of order t squared. Then in the race to infinity, it wins. So this goes to 0 because this is an exponential decay. And this is really what we're trying to look at. This is a very nice property. So in principle, if we are able to show that the variance does not grow quadratically, then we're done. And this is precisely what we do here. So you do some computation, and even better, you don't have a linear growth in n, in p, but you even have a finite variance. A finite variance is amazing because you know that your values will definitely be concentrated at some point, even if you're looking at an infinite, if you're taking the limit in that case. So we have this, and we have well, all of these just there, and in principle we should be able to bound. So let's see what our algorithm looks like, because I've promised you that we will have some mechanism or some algorithm to reconstruct the random variables. To reconstruct the equivalence relation. And so you start with the adjacency matrix, you compute it via some formula, you can prove that this is the case, and then you determine the threshold. And in principle, this should work. Let's see how this looks like for this example here. So we started from our initial example for x is equal to 1. We start with the, we computed the adjacency matrix, we computed the score for x. Now let's sort, and then we make the cut at 6. And then we obtain precisely all of our equivalence class elements back. And the very good thing about this is that this process is, in a sense, isolated. So x1 is voting for the elements which it wants to be in its equivalence classes, but it doesn't look at what the other members have to say about it. And the very fascinating thing is that they all agree in the very end. And this is what we prove if we look at the statement and the proof sketch. So as we've had so far in the discussion, we've had P is of order 1 over n. And for this discussion, again, we assume that the sizes of the equivalence classes grow linearly with n. So you can think of this as some ratio between the elements. Then we say that the equivalence relations are noise stable. And the proof is quite simple. All we need to show is that we can distinguish between the distributions of x in and x out, and we can. Because the gap grows linearly, the gap gets larger and larger. So this gets infinitely large, and the variance of this gap is finite. So if the gap if we fix n and we imagine the gap to be of length of some distance, then we know that it won't go too far away from it. And so we conclude with this. We apply the same argument that we had here. So n squared exponential of minus n, and we take the limit, and we get to 0. Now why is it? Okay. Yeah. So it's just some closing words. So there are some possible directions moving forward. You can find the critical value. You can try to improve the time and space complexity. You can explore also the noise sensitivity formula phenomena on different relations. So for example, if you look at the partial order, you can think of this as some directed graph, and then you have another interesting problem to work with. And then also there are other attacking strategies for this problem. And maybe finally I'll just share this very funny incident that happened with me. So I was working in my 3rd week on this problem. I was trying to visualize what happens to the scores under noise. And I was playing with my Jupyter notebook, and I accidentally came across this community algorithm, modularity algorithm, and I found that it always gave the right separation upon applying the noise. And I thought that was very interesting, because I was like, well, this is the solution, right? But then this is not really the case. You need to do some more work. But that is, of course, for another discussion. These are the references. And at the very end, I would like to thank and acknowledge Professor Kevan for the fruitful discussions and the mentorship that we've had so far. I would like to thank the Math Society here at Constructor University for the 3 years I've spent here, and I'd like to thank my professors and my colleagues. It's been an absolute pleasure. And I'd like to thank, of course, my friends and family. And finally, I would like to attribute this to my late friend Julius, who passed away in the summer of 2023. And none of this would have been possible without you. Thank you very much. And that's it.